Okay, thank you. Okay, yeah, thanks, Arjun, and thanks for the opportunity. This is all very pleasant and fun. So yeah, Busemann functions. I think this is a topic that you've already been discussing in your classes and talks there. So I think I can assume a lot from the audience here. There. So there are many models I could discuss here, but I'm going to concentrate on two. Most of the talk will be on the exponential corner growth model, where of course things are as ideal as possible. And then time permitting, I'll go to the directed landscape at the end of my talk. So let's just get into business here. So you've had Marci Balázs's lectures there. So you definitely are familiar with the corner growth model. Here it is again, planar lattice directed paths, i.i.d. weights on the lattice sites. And all but a few comments will be on the exponential case, so the exactly solvable case. And just make a note of my notation here. So the weights are omegas. The last passage value on the lattice is a capital L. U and V are ordered sites on the plane. And then, of course, a maximizing path is a geodesic. And when weights are continuous, like they are in the exponential case, the geodesic is unique. And the geometric object of interest now is the semi-infinite geodesic. So that's a semi-infinite path on the lattice, increasing path, so steps go up and right, with the property that it gives the geodesic between any two of its paths, any two of its points. And these are, of course, interesting because they show us how the infection travels all the way to infinity. And obvious questions arise, right? If we have semi-infinite geodesics, are they always directed? In other words, there's a well-defined sort of limiting velocity. Do they exist? Are they unique? Unique in the sense that if you pick a point and you pick a direction, can there be more than one? And what happens if you look at several of them? Do they cross each other? Do they coalesce? Do they stay apart? So these questions no doubt were posed already early on in the subject of first and last passage percolation, but serious work on them really began in the 90s. So Chuck Newman and several of his students wrote papers in the 90s about planar first passage percolation and found the first answers to these questions. And then about a decade later, his ideas migrated over to the corner growth model, the exponential case. And that's where I'll start stating now precise results. So the first ones from Pablo Ferrari, Leandro Pimentel, David Coupier, they proved that if you fix a direction xi, then there is from each point a unique xi-directed semi-infinite geodesic. And any two of them coalesce. Okay, but that's of course not the whole story. At every lattice point, there is a special direction that I'm denoting by xi star, such that in that xi star direction, there are two semi-infinite geodesics. And in fact, the two sort of split right away at x. One of them takes the E1 step and the other one takes the E2 step. And in case you never thought of this, it's heuristically kind of obvious. The uniqueness of the geodesics forces these semi-infinite geodesics to be sort of nicely monotone in the order, in their directions. So you can imagine that if you take a direction very close to north, your first step is very likely to be E2. And if you take your direction very close to east, you're pretty likely to take an E1 step first. And now as you let your direction vary, there's going to be a precise transition point where the first step jumps from E1 to E2. And in that direction, you're going to have at least two geodesics. So now these two statements seem to be a little bit in contradiction with each other, but of course not really. The full probability event of the first statement depends on the choice of the direction xi. And on the other hand, any particular xi value is a xi star value with probability 0. So these two statements can coexist perfectly nicely. But they do show us that, reveal to us that something interesting is really going on. So the question then is, what is the global picture? By global picture, I mean that you just fix the weights once and for all. In other words, you take a typical collection of weights on the entire lattice, and you try to say something about the complete collection of semi-infinite geodesics. So that's the global picture question. And then, of course, there's the question of how to access it once you try to answer the question. And that's where the Busemann process comes in. So there are Busemann functions and Busemann processes related, of course. So a Busemann function is a function on the lattice. It's associated to a particular direction xi, and it's defined by that limit there. If I move this cursor around, do you see it? And maybe I can use that to point if you can see it or not.
Yes, we can see it.
Yeah, okay, thanks. Yeah, so that limit is a non-trivial limit, as you can see. There's no normalization at all. So it may be difficult to prove, but if you can prove it, then this is what we call a Busemann function. And let me point out also one little quirk that I and my authors follow. We don't put our direction vectors on the unit circle, but instead we put them on this simplex between E2 and E1. So this here is the open line segment between E2 and E1. So our xi vectors have little L1 distance 1. So that's an individual Busemann function. And the Busemann process is then what we get when we combine all these together simultaneously in all directions. So this is a process indexed by a pair of lattice points, x and y, by a direction that's denoted by a zeta there. And then there's also a sign, plus or minus, that we use this little square to denote. And the sign is there because once we fill in all the gaps between the different directions, we can't be sure that what we get is a continuous thing, a continuous in that zeta variable. So those signs plus and minus there are for the purpose of accommodating possible discontinuities. So how could one possibly construct this thing? Well, it depends a little bit on what you start with, what you have in your hands to begin with. If you start with the exponential model, then by today's technology, proving the Busemann limits is not very difficult. So you start by proving those almost sure limits for a countable dense set of directions xi. And then there's that monotonicity coming from the fact that we're on the plane. This monotonicity enables one to take left and right limits in the direction variable. So this way you can then fill in the gaps and get the process indexed by zeta plus and minus. Now, if you start with a little bit less, say if you start with completely general i.i.d. weights, then you can't really start with the almost sure Busemann limit. But then you can use the Damer and Hanson strategy and you can start with a weak limit on a larger probability space. So one way or another, with today's ideas, one can produce this Busemann process and then hope to start using it to analyze the random growth. Now, in order to turn it into a useful tool, we would want to understand something about the process, in particular its distribution. So let me show you how we can get a hold of, or at least try to get a hold of the distribution of the Busemann process. The directedness is very useful here. And in fact, when we look at the Busemann process in a convenient way, it becomes a Markovian thing. So let me formulate it sort of as a level by level evolution. By levels on the lattice, I mean now these infinite horizontal levels. And I'm going to move vertically down level by level. This gives me a Markovian evolution. So just to have some notation for it, let me put an overbar on the omega and an overbar on the b to denote the infinite sequence of all the values on a given horizontal level. So t is the vertical coordinate there. And for each t, I have all these weights and all these b values on that given horizontal level. So for the b values, I'm only taking the nearest neighbor values. The Busemann function is additive. as you can see sort of immediately, at least from the limit definition. So it's enough to take nearest neighbor increments to understand the whole thing. So take now n directions, C1 through Cn, and imagine computing these Busemann functions. So if you want the Busemann functions on level t plus 1, all you need are the weights at level t plus 1 and above, because you're computing the Busemann functions with the limits that go northeast. So then those Busemann functions at level t plus 1 are independent of the weights at level t. And if I want the Busemann functions on level t, these guys here on the left, I can just do a calculation from the Busemann functions on one level above, that's t plus 1, and the new weights at level t. So this is simply a calculation, and I've encoded it with this mapping D. So given the Busemann values on level t plus 1 and new fresh weights on level t, I can calculate Busemanns on level t. So this gives me a Markov chain evolving sort of vertically down level by level. So now I could try to understand the joint distribution of these Busemann functions by trying to understand the invariant distribution of this Markov chain. Invariant distribution because the Busemann functions are invariant under translations, right? You can shift the weights and you get the same distributions for the Busemann functions. So here's a little theorem from my paper with Louis Fahn that if you fix the means, then this Markov chain has a unique invariant distribution that's ergodic under spatial translations. And so this gives us a starting point. So now, if we can figure out invariant distributions for this Markovian evolution, we understand, we know something about the distribution of the Busemann functions. Now, this mapping D, it's denoted by D for a very good reason. It actually has a queuing theoretic interpretation. I won't show those details now. You can see them in the paper with Louis or in other papers that I've written recently. D is for departures. And the queuing connection is that you can view these Busemann functions coming from above as arrivals and these omegas as service times. And then the D mapping calculates a departure process from given arrivals and services. And since we're in the exponential world, we're in the MM1 queuing world where lots of things can be calculated explicitly. So that's how we start getting a handle on explicit properties of the Busemann process. So let me actually show you one thing. Let's ask about the following. Let's fix a horizontal edge, say from x to x plus e1, and view this Busemann function as a random process indexed by the direction c. And I just took the plus value now so that I'm looking at a CAD-lag process. Turns out that this is a non-increasing jump process. And I'm going to give you a precise formula in a moment, but here's a picture first. Here on the horizontal axis is the simplex from E2 to E1. So the direction vector C varies along this segment here. And the red graph is the graph of this Busemann function as a function of C. So it's a jump process, see, CAD lag. So it's constant and makes jumps, it's non-decreasing. These various values here, they're all exponentially distributed. This bottom value, the last one reached, that's the weight omega x itself. So it follows from the construction of the Busemann process that if your, excuse me, if your direction vector is close enough to E1, then the geodesic takes an E1 step, and then the Busemann function is equal to the weight itself. And then as you go towards E2, the values start to increase like that. So that's what it looks like. And and there's a parameter alpha of C. So each of these values is an exponential variable, and the parameter is given by a formula alpha of C, and that's what I'm going to show you right in the next slide here. So now here's a more precise description of that process. some formulas will come, but won't be important for the sequel. So don't necessarily have to try to parse them in real time here. But I want to point out that so this Busemann function has the same distribution as a certain process that I'm calling here x. X is indexed by the unit interval, so alpha is a real number between 0 and 1. And x actually comes from a marked point process. And here is precisely how.
Timo?
Yes.
Is there an interpretation for the jump locations in terms of geodesics or something like that?
There is, and I'm going to get to that in a little bit. Yes. So the jump directions, I'll say it already, and then we'll see it soon again. The jump directions correspond to places where the coalescence point from x and x plus e1 jumps. So you can imagine this direction c sweeping out all the directions from e2 to e1. As you do so, for each direction, the geodesics from x and x plus e1 into that direction, they coalesce someplace. And the Busemann function jumps when that coalescence point jumps on the lattice. So that's what's going on behind here. Any other questions I can answer at this point? I realize I'm going somewhat fast, perhaps, but please stop me if anything comes to mind. So here are some formulas. As I said, no reason to try to remember this, but just to illustrate to you that we can say pretty nice explicit things. So here's a formula for alpha c in terms of the vector c. So it's a number between 0 and 1. And the way we construct the marked point process is that first we put on the ground an inhomogeneous Poisson point process with this intensity 1 over RdR. And we put another point at the value 1. And then at each of, sorry?
Can I ask a question? I'm sorry, I was trying to get the microphone to work when you asked if there were any other questions.
Go ahead, yeah.
Can you go back to that picture that you had on the previous slide, or maybe 2 slides?
Yep.
Yeah.
This one? Yep.
So, I just want to make sure I'm clear about what this represents, because I wasn't sure I completely understood it. So this bx, x plus e1, that's the Busemann function between x and x plus e1, right?
Yes, exactly. Yep.
So I'm probably thinking about this wrong, but I'm thinking that should be bounded because it's only going to differ by at most the passage time along one edge, and yet it seems to be going to infinity. So can you?
Yeah. So see, imagine, so your x and x plus e1, they're sort of horizontally next to each other. Now, if you take a geodesic from those 2 points to a direction very close to e2, it might take a long time before those 2 geodesics coalesce. So this value b is actually the difference between 2 very large sums of weights.
Okay, I see. It's probably my first passage intuition that's throwing me off here.
Yeah, that's right. That's right. There are some curious differences between first and last passage. Yeah, some the degree of difficulty is not monotone. In particular, since when first passage percolation, since there's no imposed direction, you can easily bound the differences of passage times. In this directed last passage percolation, that fails. And that actually creates problems.
Right, I see. Okay, thank you.
Yeah, so not every much intuition from FPP carries over to this model, but not everything. Yeah, that's a very good point to ask. Anything else I could clarify at this point? All right. So let me just flash this quickly through here. It's not worth a lot of attention, but just to demonstrate to you that we can really give a precise description of this thing. So I was building a marked point process here. I've got my points, and to each of those points, I attach independent exponentials. And then the process comes by adding up those values along the points of the point process. So basically calculating the mass of this random measure, if you want. So this is a very nice thing because it has independent increments in this xi variable. And that's very special. If I take if I take two edges, so I go from x to x plus 2e1, then already I lose that property. But there is an important qualitative property which I want to highlight with this corollary. Since the Busemann process is additive, any value, for any 2 points x and y, if I look at it as a function of xi, it is still a jump process. And by jump process, I mean now that those jumps do not accumulate anywhere except at the two endpoints, E2 and E1. So at least if you stay away from the endpoints, it's a very nice regular thing. And now I want to actually address Arjun's question a little bit. I want to show you how this jump process property connects up with geometric properties of geodesics. So I want to show you, not really precisely, but at least heuristically, how these Busemann singularities are connected with non-uniqueness of semi-infinite geodesics. So the starting point is that we have these countably many nice directions. Remember that for any fixed direction, we can prove all the nice properties with probability 1. Unique geodesics coalescing. So we can do that for a countable dense set of directions. So that gives us sort of a skeleton around which we can then build, and we can try to fill in the gaps between these nice directions. So let Z superscript xi denote the point where the xi geodesics from x and y coalesce. Okay. Now, then this formula arises. See, when you calculate the Busemann limit, remember you're taking geodesics from x and from y. Once those geodesics coalesce, you can stop right there. You don't have to go any further because that now you've taken the limit. So the Busemann value in direction xi from x and y is the difference of the last passage values from x and y to the point of coalescence. So we get this finite formula. All right. And now here comes a little technical point. Since the weight has continuous distribution, if I tell you that there is a coalescence point, then this b value on the left and the coalescence point determine each other. Obviously, if I tell you the coalescence point, I've calculated the left-hand side. But why does the left-hand side determine where the coalescence point is? Well, with continuous weights, I can assume with probability 1 that all finite linear combinations with integer coefficients are non-zero. So then there are no two finite paths on the lattice with the same total weight. And that's why these two sides sort of determine each other. And now, so in particular, these two functions of xi on the left and on the right, they share their constant intervals and the points where they jump. So now, since I know that the bxi is a nice jump function, a nice function that is constant and then has left and right limits, I can start taking left and right limits from my good directions. And everything works out as beautifully as it possibly can. The geodesics are monotone, so the geodesics converge on the lattice. My b values come from a jump process, left and right limits exist. So it follows that these z points, these coalescence points, they also converge because they're constant in an interval, and then you go to the endpoints, and of course it doesn't jump anywhere. You get the limits. So in other words, from this initial skeleton of geodesics in the good directions, we can now get a sort of a full collection of geodesics in all directions with this plus minus correction, because we don't know if limits coming from both sides actually come together. There can be jumps. And indeed, there will be jumps because we know that the B process jumps. I just gave you explicit formula. They jump, those jump. And when the B process jumps, because of this identity up here, the coalescence points must jump. And when the coalescence point jumps, at least from one of those 2 points, X or Y, there's got to be a non-unique geodesic. Now, To understand that requires you to draw a few pictures, perhaps, but that is a fact. So this way, jumps of the Busemann function implies that, or tells us that in those jump directions, there are non-unique semi-infinite geodesics. And it works the other way also with a slightly different argument. If you have non-unique geodesics, you're going to see a jump someplace in the Busemann process. So this kind of reasoning you can now carry out a lot more. And I will now summarize results for the exponential corner growth model that we can get out of this. So this is a theorem on the global existence, uniqueness, and coalescence in the exponential corner growth model. And it's in this paper with Krishnan that is due to appear in GEMS sometime soon. So the basic situation or the basic lesson is the following, that this entire set of directions decomposes into two sets. There is the good set, and then there is the sort of the bad or the exceptional set. The exceptional set is a countable dense set, and it's random. And the situation has these features that in the good directions, from every point, there's a unique geodesic, and all those coalesce. So in a good direction, there's a single coalescing tree of geodesics. In the exceptional directions, there are exactly two coalescing trees. So from each point, there are two geodesics, the plus geodesic and the minus geodesic in each one of these exceptional directions. Now, those geodesics don't have to separate immediately from X. They may travel together for a while, but eventually they separate. And then the plus geodesics form one coalescing tree, and the minus geodesics form another coalescing tree. And then we have a couple characterizations of this exceptional set. As already kind of alluded to, it is the set of all the jumps of the Busemann functions. And it's also the set of these C star values, which for those who know, let me say that they are the asymptotic directions of the competition interfaces. That's a notion that I can't really go into now, but I think many of you know what I mean there. Any questions about this theorem? So I have a few more bullet points about it. So this accounts for all the semi-infinite geodesics on the lattice. The only thing that's missing are the trivial ones, namely those that are just straight lines all the way to infinity. So in particular, every semi-infinite geodesic has a direction, and only these trivial ones have directions E1 and E2. Every other geodesic has a direction into the interior of that line segment. And then there's the very non-trivial fact that nowhere on the lattice are there three disjoint geodesics in the same direction. And the reason is that if you have three geodesics, then two of those have to be either a plus or a minus, and then they coalesce. So I want to highlight this last bullet a little bit more, that we cannot yet prove from the Busemann process. We rely here on a very deep result of David Coupier. He proved that from a single initial point, from a given initial point, there cannot be three geodesics in the same direction. And then we improved it to this statement that you can't have anywhere on the lattice. The thing about Coupier's result is that there's no proof that would just use the corner growth model itself. Coupier's proof relies crucially on some results about the Taysep speed process from a little over a decade ago. And it would be wonderful to be able to prove Coupier's result without leaving the context of the corner growth model, because then we could prove the same thing for many other models also. So that's a really worthwhile open problem now. All right. So that's the overall picture on the exponential corner growth model. Any questions, comments here? Now, what this tells, one thing we learned along the way here is that those Busemann jumps are really crucial for the overall geometric picture of the geodesics. So it would be interesting to try to say something about the distribution of the jumps on the lattice. Oh, oops, sorry, I was getting ahead of myself. I inserted another new slide here actually compared to the previous versions of this talk. I figured you might want to ask at this point, well, what if we drop the assumption of exponential weights? What can we say for general continuous i.i.d. weights? We can recover this picture almost in full, basically everything except Coupier's result, if we make two hypotheses. And of course, these are going to be big hypotheses, something we cannot verify at present, but at least I can tell you what exactly our proof uses. We use one hypothesis about the shape function, namely either assume that it's strictly concave, or if you want to allow flat spots, then assume that the endpoints of the flat segments are points of differentiability. And then we assume that the Busemann functions are these jump processes. Under those two hypotheses, we get that whole picture of the geometry of the geodesics, except the restriction of just two coalescing families. We can't rule out the third one because we don't have Coupier's result in the general case. Now, for various LPP-related models, the Busemann functions have now been described. If you want to know more, ask Evan, for example, about the Brownian LPP. And wherever we understand the process, these two properties hold. So maybe there's some chance that these are generally true. All right. Now I'll jump back into the exponential case.
Timo?
Yes.
What is the significance of the accumulation at the extremes?
Significance. I'm not sure what you mean by significance.
Meaning, geometrically, does it say something about the behavior of geodesics? Or?
Well, yeah, I guess you can imagine again, take 2 points horizontally separated and think of their geodesic into directions that are converging to E2. So as you're getting closer and closer to E2, the jump locations will go further and further away. And probably converge sort of asymptotically, go into the E2 direction, but further and further away. So that corresponds to those jumps accumulating at the endpoint there. I don't think I have anything more clever to say about that.
Would the, I mean, suppose there's an accumulation point in the interior, does that?
That's exactly, thank you. I should have addressed that point. So let's go back to this slide here. So I should have really highlighted here that, see, this breaks down if we don't know this regularity about the Busemann function. So what I said here relied crucially on the fact that I knew that this Busemann function here has isolated jump points. If we assume that there's an accumulation point in the jumps in the interior, then what I can tell you is that as you take that direction C towards that accumulation point, the coalescence points escape to infinity. And if the jump locations of the Busemann function accumulate from the right, then these coalescence points run off to infinity on the right and vice versa on the left. So there is a very, very precise connection here between the regularity properties of the Busemann process and the coalescence properties of the geodesics. So this is the kind of things that we elaborate on in that GEMS paper. But that was a very, very apropos question, because I did mean to highlight this point. Thanks. Maybe you were reading my thoughts, in fact. Anything else I could address at this point? All right. So I was going to say something about the spatial distribution of the Busemann jumps. We cannot say anything spatial genuinely yet, but at least we have something interesting about these jumps on the x-axis. So let me again consider these nearest neighbor Busemann values on the x-axis, and let me abbreviate a little bit like this. So the index k marks one of the nearest neighbor edges on the x-axis. And so this is, again, these are functions of the direction xi. Now, given a xi, this xi may be a jump point at various locations k. Let the tau indices mark those jump locations. So for a given xi, the taus are the indices k where the Busemann function jumps at xi at the edge marked by k. Now, of course, only at most countably many of these xi values are jump points. So for those that are not jump points, the taus are not defined, or you can just take them to be, say, minus infinity on the left and plus infinity on the right. So the taus are relevant only when there are jumps. Any questions about that notation there? So I want to understand now something about these tau values. So let's think this through a little bit before I flash the theorem. So remember that any particular xi value is a jump value with probability 0. So I cannot, at least immediately, I can't really condition on xi being a jump location and then start reasoning from that. Plus the x's are dense. So the x's themselves don't form a good point process because they're dense on the interval of jump locations, of directions, sorry. However, now comes the fact that the xi values on a given edge, the xi values don't accumulate except at the endpoints. So if I consider the point process of locations and jump values, I get a decent object. They don't accumulate. So I think of a point process now that lives on infinitely many copies of the interval of xi values. One copy attached to each nearest neighbor edge on the lattice. This way I have a decent point process. And now I can use a palm kernel to condition on seeing a jump at xi. So I can't stop to tell you what palm kernels are if you've never looked at the theory of random measures. So you can just take this to mean conditioning. That's perfectly good. But there is a particular technology called the palm kernels in the theory of random measures for doing this kind of conditioning. So now I can tell you what we can say. So condition on xi being a jump direction at the origin. So at the edge from the origin to E1. Then if you look at this process of increments between successive xi jumps and the values, the sizes of the jumps themselves, this is an i.i.d sequence. Okay. Furthermore, it has the following marginal distribution. So, so this double vertical line here just means the palm conditioning. So I have the condition here on the right side of that double vertical line. And on the left, I'm saying that the distance between the ith and the I plus first occurrence of a jump at xi is n, and the size of the jump in the Busemann value is at least r. That probability is given by this expression here. So notice the size of the jump is again an exponential, and there's that alpha xi parameter that whizzed by before when I showed you the marked point process. And then there's this distribution for these discrete values, these discrete distances between the successive locations where xi is a jump. So there's a Catalan number, if you forgot the formula, it's down there, and then this power of 2. Now, turns out that this distribution here for n, this is a well-known thing from classical probability. And dare I ask if anyone in the audience knows what it is? Those who've read our paper are not allowed to answer. I can't see hands or anything because I only see a sort of a panoramic picture of the whole room there, but Maybe Arjun can say, is anyone raising a hand? Does anyone know that distribution? I guess maybe not, or then nobody dares to answer. That
No.
is, sorry?
No, there are no hands raised, but
No
maybe
hands,
someone
okay.
knows, yeah.
This is the renewal process of simple symmetric random walk. Precisely speaking, this is the distribution between successive visits to zero by simple symmetric random walk. Now, simple random walk cannot visit the origin at odd times, so you have to sample it at even times. So you sample simple symmetric random walk at even times. This is the distribution between the visits to zero. So in other words, this was quite a surprise to us. All of a sudden, we see simple random walk arising here in this KPZ model. We were quite pleased and excited by that. So these jump locations come like zeros of simple random walk. So in particular, one can get various quantitative conclusions from this, that, for example, if you look at a large interval of order n, size of order n, then each of these jump locations appears there roughly square root n number many times. Of course, they don't all come at the same frequency, and you have to take the interval bigger and bigger, but roughly speaking, that is the case. All right. Any questions about this result? I wish I could tell you where the random walk lives in the corner growth model, if it does. At this level, this is just a recognition that that this is the formula for the renewal process of random walk. So it's purely at the level of formulas here, nothing else. Okay, so up to this point, I've been telling you things about the corner growth model and its Busemann process. The Busemann process is also a tool. It's a very useful tool for proving things. So now I'm going to show you a few applications of it. The applications always use the fact that when you have a stationary growth model with explicit invariant distributions, you can do calculations with it. And then you can use the monotonicity to bound, say, the bulk process with i.i.d. weights. And with the Busemann process, you can couple more than one stationary version together in a stationary way. So that gives additional power. So now I'm going to just flash 3 applications at you and not really tell you any details because time is running, so I have to be pretty efficient here. The first application has to do with coalescence estimates. So start 2 semi-infinite geodesics in the same direction and start them so that they are k to the 2/3 apart. K is some integer here. So roughly speaking, k to the 2/3 apart. And then you ask, how fast do they coalesce? Well, you know from KPZ lore that these geodesics should fluctuate with an exponent 3/2. So if we start them k to the 2/3 apart, they should coalesce at a distance order k. So here we have probability bounds, both on coalescing too late and coalescing too soon. So the first bounds here are for coalescing too late. So here capital R is large, and you ask about the probability that you don't coalesce before going distance r times k. So that probability goes down like r to the negative 2/3. And then the other case is that where you ask for a small r, you ask that you coalesce too soon, that you coalesce before you reach distance r to the k. So that probability goes down like e to the negative constant times r to the negative 2. If you want to know more about this work, this is work with Xiao Shen, who is right there with you. He can tell you about this. So this proof used a number of inputs, and among them was this joint Busemann distribution. And you notice our proof for long time coalescence is not quite ideal. We have this logarithmic blemish here. That's the price we paid for not using interval probability. And the sharp result was proved earlier by Riddhi and Surav Sarkar and Alan Sly in their 2019 paper. So that's coalescence, the first application. My next application is to bi-infinite geodesics. You may be aware that already in the 80s, people were wondering whether bi-infinite geodesics exist. Back then, of course, the question concerned first passage percolation, planar first passage percolation. And this question remained open until it was proved for exponential corner growth model. And of course, the theorem is that there aren't any non-trivial bi-infinite geodesics. You have to throw in the word non-trivial because, again, those bi-infinite lines, those horizontal and vertical lines, those are bi-infinite geodesics. So this was first proved by Riddhi and Hoffman and Sly. And then 10 months later, Marci Balas, Ofer Busani, and I proved it. Again, a key point in our proof was the joint Busemann distribution. And then afterwards, the result was also proved for the geometric corner growth model by Firas, Chris, and Firas' student, Sean Grothaus. So the proof idea is what I just said, that you use the stationary LPP process to control the i.i.d. one. And our proof also extends to positive temperature. So let me here in this one single slide touch briefly upon positive temperature. You know what this means by now, at least on some level from Jura's talk yesterday. So now I'm on the lattice. So I'm thinking of a directed polymer on the lattice. When you go from zero temperature last passage percolation to positive temperature polymer on the lattice, you don't choose a unique geodesic. Instead, you have a random geodesic, so to speak. So the weights now give probabilities. So between 2 points U and V, the probability of a path gamma is now the product of the weights along it divided by the normalization that makes it into a probability, the partition function. And semi-infinite geodesics or infinite geodesics are now replaced by polymer Gibbs measures. So a measure on infinite paths, semi-infinite or bi-infinite paths, is a Gibbs measure if its conditional probabilities are given by these quenched distributions. So you condition the infinite path measure on 2 points lying on the path, and you ask about the probability of the path segment between the 2 points, and that should be given by the quenched polymer distribution. And then the theorem with Ofer Busani is that with probability 1, the inverse gamma polymer model has no non-trivial bi-infinite Gibbs measures. So again, you have to put that non-trivial business there because you have these flat lines. All right, so those were my applications of the Busemann process. So of course, for this result here, we have to prove something about the Busemann process for a positive temperature polymer. So results analogous to the ones that I've shown you about the exponential corner growth model are valid there also. Now, this concludes the part of my talk that focuses on the corner growth model. And I'm almost out of time here. So maybe I'll take 5-6 minutes and quickly try to say something about the directed landscape. So the directed landscape is a continuum last passage percolation model. And it is the scaling limit, the putative universal scaling limit of all the planar models in the KPZ class. So, and I'm denoting it by this script L, obviously notation inherited from Duncan's and Daverne-Ortmann-Virag's seminal paper. So here, for example, I'm stating the limit result for the corner growth model. I've colored the time variables S and T and the space variables X and Y so that you have some sense of how they appear in the limit. So here I'm taking the special case where I'm going along the diagonal. So you see, I'm going along the diagonal. That's the time direction. And then from the diagonal, I'm deviating laterally in the space direction on the order n to the 2/3 with these variables x and y. And then you subtract the right things to center it, and then you divide by n to the 1/3, the KPZ exponent, and that's the way that the directed landscape arises. In addition to the directed landscape, another protagonist in this story or this picture is the KPZ fixed point. So Matetsky, Quastel, and Remennik introduced it some 5 years ago at this point, or maybe almost 6 years ago. And they introduced it by giving formulas for the transition probabilities. It's a Markov process. So they gave determinantal formulas. But it also has this beautiful connection with the directed landscape, namely this variational formula here, which is like a Lax, Oleinik, Hamilton, Jacobi formula. This formula was proved later by Mihai Nika, Jeremy, and Daniel Remennik. So this is the formula that's relevant for us now. So now I want to ask about the Busemann process of the directed landscape. The story is very analogous to what I've already told you about the corner growth model. In particular, to get the Busemann process, you want to start with Busemann functions. And to our great fortune, we didn't have to build the Busemann functions because Mustasaar, Rahman, and Balint Virag did it for us just around the same time as we started working on this. So they constructed these individual Busemann functions. And here's the limit definition again. So you see, you pick a direction xi. Xi is now a real number because you can go into any of the directions, northerly directions. So xi is a real number now, and then u is a time parameter that's going to infinity. So you go sort of northward, but at a slope xi, and this defines an individual Busemann function w sub xi. And then it goes just like before. We fill in the gaps of the good directions, and we get a Busemann process, again indexed by directions, these space-time quadruples, and signs plus or minus. And just like before, we want to ask, can we say something about the distribution of these things? Now, already Raman and Virag knew that if I take S equals T here in this Busemann function, then this is a Brownian motion with diffusion constant square root 2 and drift 2 times c. So the distribution of an individual Busemann function on a fixed time level was known. Now, to get the joint distribution, the picture is very much like before. Remember, in the corner growth model, the Busemann function evolved sort of vertically downwards in a Markovian fashion. The same is true here also. The Busemann functions evolve backward under the KPZ fixed point. So the question is, can we find the joint Busemann distribution by understanding some kind of a multidimensional invariant distribution for the KPZ fixed point? Again, already some time ago, Leandro Pimentel and others have known that a single Brownian motion with drift is invariant for the KPZ fixed point. So it of course goes together with what I said up here about Brownian motion with drift. So that's what I'm going to show you now in the last few minutes. Our work starts by finding this multidimensional invariant distribution. This object is called stationary horizon. It was discovered or invented by Ofer Busani, and he gave the name. So let's use his name for the object. This thing is a Cadillac process whose states are continuous functions. So the paths indexed by the xi variable are in the D space with state values in the space of continuous functions. These individual states are in fact Brownian motions with drift. And to describe it fully, I need to tell you how to construct the finite dimensional distribution. So it goes by a mapping. The mapping takes as input a bunch of independent Brownian motions with drift. So here I have Brownian motions with diffusion constant square root 2 and drifts 2 times xi. So I take n of them. And then I map them in a very specific way. That's the right-hand side here. This constructs the finite dimensional distribution of the stationary horizon. So this vector on the left here is a vector of n continuous functions on the real line. And these psi-k mappings that appear here on the right-hand side, these are centered Brownian last passage values. So here's a formula. And again, if this is new to you, please don't try to parse it. It's enough to know that there's an explicit formula. But let me tell you some properties of this object. So this process, as I mentioned already, each individual state value is a Brownian motion with drift. So that's what I'm saying here. Again, diffusivity square root 2, drift 2c. They're coupled together in a very monotone fashion. Let me actually first look at this lower statement here. If you fix the points x and y, and you look at the increment as a function of this parameter xi, then that is a non-decreasing jump process. Excuse me. So again, constant for a while, jumps constant for a while. And each pair of these guys agrees in a neighborhood of the origin. So this tells you something qualitative about how this is a process of coupled Brownian motions with drift. I'll show you a picture in just a moment after this last paragraph here. I just want to tell you again where this is coming from. So Ofer-Busani derived this first. And what he did was he took the exponential, the Busemann process of the exponential corner growth model that I was describing to you before, and he looked along the diagonal direction and then scaled it in the manner that you would scale when you go to a KPZ limit. So it's very much, of course, connected to the way you go to the directed landscape from the last passage percolation process. And so Ofer's paper came on the archive last October. And around the same time, Evan and I were finishing up our work on the Busemann process of the Brownian last passage percolation. And when we saw Ofer's paper, we realized that, my God, we had discovered the same object. So that already gave us some sense that there's some universality there in the thing that Ofer discovered. And then we set out we sort of had a hunch that maybe that's the Busemann process of the directed landscape, and we set out to prove that, and that's what we have now. So there's a picture of the stationary horizon. The graphs of different colors, those are the GXi state for different values of Xi. And they all go through the origin. That's just by definition. They're two-sided Brownian motions with drift, so they're all pinned at the origin. But they also, every pair agrees for a while around the origin in a non-trivial interval. Not maybe so terribly well visible, but it's true anyway. And I'm basically out of time, so let me just flash you the last two slides here very quickly. So our theorem is that if you run the KPZ fixed point from the stationary horizon, in other words, now you have basically uncountable any number of parameters Xi, and you take one of these stationary horizon states as your initial state for the KPZ fixed point, then the joint distribution is preserved. And the KPZ fixed point, there's a sort of a global time shift, so you have to center them by subtracting the value at the origin so that you get a function that's 0 at 0. So there's the invariance. There's also a uniqueness statement. This gives the unique invariant distribution subject to having the right asymptotic slope. And the proof of this goes, first of all, we rely, of course, on Duncan's and Balin's work that couples the directed landscape with the corner growth model. And then we use Ofer's stationary horizon limit of the corner growth model. And I should add that this is not the first uniqueness result. Leandro Pimentel proved a uniqueness result for the single Brownian motion as a steady state for the KPZ fixed point but this result of ours strengthens his uniqueness theorem also. And then out of this comes the key corollary that if I fix a time level t and I look at the Busemann function as a function of this initial spatial coordinate, and I let xi vary, then the distribution is exactly the stationary horizon. So now this sets the stage just like in the corner growth model, and then we proceed to derive various results that are quite analogous to what we could do in the corner growth model. We characterize non-uniqueness of geodesics as the jumps of the Busemann process and so on and so forth. So I have overstayed my welcome now, so I thank you very much for your attention. And that's the end of my talk. Thanks.
There any questions for Timo? So I have a question, Timo, and this goes back to the competition interface you showed us for the corner growth model. Do you so when you see these competition interfaces, do they stick right next to each other as they progress along the lattice, or is there some space between these competition interfaces? They fluctuate.
You're thinking now of the competition interface. Oh, you're thinking of the paths themselves.
The geodesics themselves, yes.
You mean the competition interface paths?
Right. Are they geodesics or are they just?
Well, so yeah, we've been trying to look at that. So if you look at the i.i.d. bulk corner growth model, I don't think that the competition interface paths are geodesics. It's sort of tantalizing to think that there should be some kind of a stationary description of them, but I don't know of one. Now, but if I do something a little different, and now this will be unintelligible to many of you perhaps, but if I take a stationary corner growth model, I start with a boundary, for example, the x-axis, and I do a stationary corner growth model, then I can again draw competition interfaces by sort of asking from which points do the geodesics land on one side of a point on the boundary as opposed to the other side. So this gives another notion of a competition interface now in the context of a stationary corner growth model. Those competition interfaces are also geodesics. So there's this notion of dual weights when you have a stationary corner growth model. So if you flip between original weights and dual weights, then semi-infinite geodesics and competition interfaces trade labels. So in that situation, the competition interfaces are geodesics, but I don't know about the i.i.d. situation.
If there are no further questions, let's thank Timo again.
All right, thanks everybody.